for me. Okay. Hello, everyone. So we're Team Hypercell. Thank you for coming today. So architecture today is usually developed as static objects. While the world is very dynamic, we were interested in developing a system that can respond to change through self-awareness, mobility, softness, and reconfigurability. A time-based system that has no final form, but rather in continuous formation. Our system is an ecology of constant change and reconfigurability. We develop mechanisms to address these changes based on local decision making. Our system exhibits mobility, aggregation, and structure generation. Through local interaction, they are able to create spaces. We studied mass population and their behavior, how in ecology they are able to collectively create structures. So this is an overview of our system. We have the single and the collective. In the single, we have transformation, self-assembly, and energy collection. In the collective, organization, self-structuring, and space making.
We initially started our design research through investigating local interaction between two bodies. Through the use of magnetic patterns, we were able to understand how two bodies can interact by changing the polarity of the magnets. Here we can see how one cube is able to interact with another one. We were also interested in the self-awareness of the cells and developed strategies of bespoke face-to-face connection. Computational strategies of self-assembly were developed to demonstrate the ability of the cells to assemble into aggregation by local face-to-face decision-making. We also developed larger populations with goal-oriented strategies. In these catalogs, you can see aggregations of these face-to-face connections and larger body formations. And this is one of our first prototypes that exhibits the need for a flexible, soft body that can connect and disconnect according to its facial conditions. So we achieved this with a simple shape that is able to compress, store energy, and pop back in its initial shape. The cell was fabricated from a single flat sheet, and by connecting the edges, we create its final form. We explore the behavior of a number of models created with different patterns. These patterns gave various flexibility to the component, which in turn resonates into its mobility and ability to self-structure. This portion of the research was concluded with the most flexible and simultaneously the most mobile cell. The flexibility of the shape can enable the movement of one cell on top of the other one. This is the first and basic action upon which we developed our strategies of self-assembly. The first prototype we developed shows the movement of the cell from one cell to another mechanically.
After making lots of iterations with material wood, we changed our fabrication technique to 3D printing, and we analyze lots of different kind of forms and shape to get the best outcome for it to roll and climb. After the first iteration, we achieved this shape, and we designed this rolling mechanism that is based on two continuous servo, and it's possible to move to 4 different directions. One of the servos controlling the central weight, and the other one gives the direction to roll. After seeing the limitation of the continuous servos, we changed the inner mechanism to achieve more agile prototype that is based on 6 linear actuators communicating with each other to change the inner mass and creating the motion. This is the first prototype we made with linear actuator. It's not only creating motion, but also the softer skin enables us to change the shape to let it be more stable or be in more motion. We see energy as a part of our autonomous system, so we design our skin with graphene battery and flexible solar panels that it can collect energy and keep the system working. This is the basic prototype to show how it can open its skin and close back to move forward. This prototype shows how each cell can open and close in different times to gain electricity to keep the system running. After we made lots of iterations, we created the catalog how the cells can open itself according to its condition. This is our first climbing model using face-to-face connections with electromagnets, and through the simultaneous actions they are able to climb one on top of the other one. The limitation of this prototype is all the electronic system was out of the prototype itself. In the next iteration, we try to minimize everything and we put all the electronics, battery, linear actuators into one cell, and we refined our shape to achieve more flexibility. Through these refinements, we are able to do the same actions without an external power supply. We also designed how we imagine our final shape, and it's made out of a softer outer skin and a harder shell as well. This simulation shows how each part of our design system can be assembled together. It's made out of a single steel core and 6 linear actuators, which each can take up to 100 kilogram force and 25 kilogram shear force. And there are some nano actuators which led it to rotate in 360 degree. And the bigger hydraulic system enables high power, at the same time a smooth continuous motion. At the same time, because of the shell and the outer skin is flexible, we are able to achieve different kind of outer shape to make the cell more stable or help itself to move more easily. After it's getting a circular shape, it can rotate its own inner weight and move freely. This is the overview of our single cell functionality, and it can be stable, self-assemble, and be stable again when it's get into its last position. This overview shows us that cells need to have continuous communication in between and also simultaneous action to achieve this self-assembly.
So we developed mobility techniques for the single, the collective, and the crowd in different exercises for both. So in this one, you can see a single cell moving accurately and how it can move to a target. And if the target is light, how it's able to move more smoothly, navigating through. And finally, how it's able to follow light and sense obstacles and avoid them. Working through these strategies, we developed other strategies of how many cells can connect together to create bodies to move and conserve energy. And showing the same behavior in the prototype for 2. And for 3. And as a bigger body, they are able to move together. When they're low on energy, some of them are able to open, collect energy, while the others continuously move. As individual cells, they're able to collectively move, connect, and create different formations. And these ideas resonate in the simulations when we have 2 groups and showing how 2 groups can avoid each other. And how 2 different groups can merge and avoid the other 2 groups. And as a big population, we call this play mode, where they don't have a specific criteria or target, but they're just there to exist and enjoy themselves as an ecology, I guess. And also how they're able to sort themselves when they reach specific configuration. Here they have like a body plan they need to form. So this is how they sort themselves into it. Coming in as different groups, and while others are giving them more space to join.
So we developed a 2-to-1 prototype, and here we can see how more than one cell is able to interact in order to achieve the climbing and to collectively take a decision to allow a space for the moving unit. And in this simulation, you can see the movements that this cell is doing. So you can see how these units are self-aware and how they understand where each cell is and which is the active phase. Every single unit is 10 centimeters. So this prototype is 2-to-1, which you can see. And this is a more advanced prototype that it's able to perform climbing, ladder up and down. We developed a local rule set found out in the prototypes and explored 3 time-based building strategies according to the energy consumption of the cells. A stair-like structure leads to a minimum overall energy consumption, where the new cell and the existing cell spend almost the same amount of energy. If time is vital, there is a possibility that the cell can choose the shortest path. So in this case, the system responds to the new cell and rearranges itself in order to help the climbing procedure. In this case, the existing unit spent almost double of the energy that the new cell does. And in the case of the collaborative motion, we need at least 2 cells in order for them to move up. And the system almost does not spend any of its energy, but however, the amount of energy that it's required from the new cells, it's almost double from the other scenarios. So all in all, the first strategy is the best overall of the 3 because of its overall energy consumption, which is the lowest one. But however, the 2 other scenarios are good if time is essential, or in the last case, if the existing system does not have any energy to spend, so it can only depend on the new cells. We aim to achieve the same goal, but using the 3 previous strategies. So vertical arrangements were created according to the time of assembly and the population of the cells. Following the local level rules applied many times led to these formations. So the stair-like pattern strategy required the least number of components to reach the same height. We needed around 460 cells and 18 minutes to reach this height. The next one is the shortest path, and the time of assembly is the quickest of all 3. However, it needs almost 100 cells more to achieve the same goal, like in 12 minutes. The hybrid has the same almost number as the ladder strategy, but the speed of the shortest path. So we investigated this strategy more, and we created a variation of vertical aggregations according to the previous logic. So these aggregations incorporate the hybrid pattern of assembly, as we said, and we have these aggregations which are distorted and spiraling, where you can see that the pattern is consistent, so this resonates into a higher speed of assembly and symmetricality. So the system, in order to make one of these aggregations, which is around 7 meters high, totally spends energy which is equal to 5 50-volt light bulbs running for an hour. And this structure is created for around 2 hours and 30 minutes. We took an example of the symmetrical aggregations in order to examine the climbing logic of the cells. And we can see that how they sort themselves in order to choose which way they're going to climb up. The cell structuring of the base layers are being created when the ground is not flat. So they're trying to achieve the same height, and then they're ready to start the building process. We were also interested in not only how they grow vertically, but how can they possibly create a cover space. So these are the initial steps for the horizontal growth. And here you can see how these cells come into position in order to create some configurations like urban furniture. And how the same configuration disassembles and the same number of particles can make space for more people.
We started to see the population and its possibilities of aggregation to define the type of formations and specifically what a population can do. So here you can see the 40, the 100, and the 200, and the 1,000. And if we assign them a goal, they're able to find that goal. Which is here, it's a horizontal goal, so they learn which direction to go according to that. And this is a catalog that shows the populations and what a population can do from 100, 200, 400, 500, and to 1,000.
Move on to a much larger population scale. We start to investigate the space-making logic of our system, which is based on local decision-making and biased by global information. First, each cell is aware of the energy condition of itself as well as its neighbors. Based on this information, they are able to make decisions on which kind of building strategy to choose. If the energy is sufficient, they prefer to use the shortest path to reach the higher building speed. And if in the case the energy is lower, they might stay in position and wait for steps. Structure is another important aspect of the system. Load analysis is performed to define which part of the structure is redundant and which part of the structure is unstable. And for a face-to-face connected structure, it's important to eliminate tension connections. So whenever tensile forces are bigger than its threshold, reinforcement will be required. This simulation shows how cells collectively grow vertically based on local information. Cells are building itself at different building speed and trajectories. And this view shows the energy consumption map throughout the building process. This is the load analysis, where load trying to find the shortest path linked to the ground, and the green lines are the compression and red lines are the tension. And based on this information, the system is aware of the redundancy distribution of itself. More complex, different kinds of structures can be created if the cells decide not only to grow vertically, but also horizontally. This catalog shows the different possibilities. And energy and structure are not the only criteria of the system. If we can also introduce some more building criteria like the coverage and ground occupancy. And the redundancy of the system is important because it provides free cells that is able to migrate either to create spaces or to help reinforce. This is the simulation that shows a reconfigurable space-making process. We think it's not just a one-way build-up process. While it's growing up, it's aware of the stability of itself, and temporary scaffold will be created to support the structure. Once they converge to a stable position, temporary scaffold will be removed. And cells are also aware of the partitioning of itself. This is the load structure analysis of the structure. and redundant cells are free to migrate to other places. To respond to a real-timely changing built environment, parts of the structure might be removed according to different requirements and goals. The cells that travels from the removed structure may go to the surrounding structures to reinforce. And they can also make decisions on build up some more structures from the existing structure. So the redundant cells are free to participate in new constructing process. Every time the structure is changed, the structure analysis is performed to update the redundancy information. And this is the overview of our system, how cells come to the position and start to generate spaces. So the whole structure is not a finite shape, but is a constantly reconfiguring system. Thank you.
Thank you. These are the large population models that were latestly generated. These are the opening and closing catalogs. This is the newest design of our cell. These are the early models we did back then. These are other aggregations we've done. This one is our prototype pavilion. And these are all the prototypes we've worked throughout the year. And these are one of also of our early studies in space making. Which one do you want? The latest one. Ah. I think this one's, it's based off of this one. And this is the
for once in 2 days, I'm actually sort of speechless, to be honest with you. And that's a compliment to you, son. What an extraordinary project! What an extraordinary presentation! You know, all of the artifacts are sort of beyond belief in a way. I think, which is really what you want here. And my questions are much more, or my comments are much more, I would say, maybe related to some topics that we've had. Motivators would be one, I guess. You know, you've established a kind of, you've really, in a certain way, I really wish John Fraser was here to see this project, because you have built the, you know, you have fulfilled somehow the dream, let's say, to a certain point, right? Or you're getting closer, which I think is extraordinary. But I'm really interested, of course, in the steps by which the motivators of these structures begin to happen. The kind of communication between a kind of swarm network and a human-driven network. I'm really impressed with the cross-linking and communication that you're beginning to establish between the cells. I think that is really commendable. But it's just not clear yet what the connection, the communication protocol is between. I'm assuming these are for humans. I mean, no one's really brought up the idea that maybe we're actually not building these structures really for humans. We're building them for other robots. We don't really know what the motivators are. But I'm actually super curious about that. How do you make sure this isn't just another kind of top-down project, but that in fact there's a kind of bottom-up communication, you know, and clearly you're thinking that way. I mean, one of the most, for me, impressive parts about the project, and of course the letdown of you probably having to plot these. I wish those were LED screens, because they're so impressive when they're vibrating and you're planning that, right? Yeah. You're going to spend your last few dollars on those. But the kind of vibrational kind of quality of the project, I think, for me, is the most extraordinary. Understanding that it's in a constant state of kind of evolution, for me, is really one of the most promising parts. That I think you thought the project through to that level, and a lot of the other projects just didn't really have the self-confidence, let's say, to really push it, you know, that far. So really, my big thing right now is just the kind of the communication. It's a sort of subject that, when I see the work, all of the body of the work, the behavioral aspect of the work, in a conversation that Patrick and I were just having, how do you foresee, let's say, that happening? I know that there's a motivator behind these. It's highly geometric. It's based on previous systems, right? I mean, those look like, you know, masonry block-like structures that we've seen. These would have their own kind of capacity. So I'm just trying to understand what would that motivational cycle look like? Assuming that these are for human occupation, how would they read humans? Do they know a language? Which language do these things communicate? I mean, are you able to speak to them in English or in some other coded language? Are they understanding a sign language? Is it a gesture control? Mind control? There's all of these ways that we can begin to understand our kind of motivation. It reads my nervousness, right? You know, so it's another avenue, right?
It's so much on the table that this could be the next iteration of this. You know, you have these wonderful swarm of elements which coalesce into these structures, which evolve continuously. I mean, I was on the floor in the first minutes, and I wonder if you can top that, and in the end, you topped it with this vision of what this becomes. I mean, really, really incredibly rewarding and humbling to watch you guys. And I think if you had if the question of the interaction with human populations, that, you know, you throw them in, you have the capacity, you have already creating agent swarms, and we are just another set of agent swarms you can analyze in exactly the same way with respect to our capacities, limitations, energy requirements, trajectories, scheduled protocols, you know. You talked about these creatures like this. You know, look at them. At the moment, they're just enjoying themselves. They kind of just let their muscles flex and roam, and then there's a task coming along. And I mean, we are like that, and you know, that can be thrown in there, and suddenly there's a kind of several populations. You had groups out of the same units meeting and breaking up, and I just invite you to bring in the next population. I mean, that is us. And we are males and females, and that will be differentiated. The differentiation of these swarms, I think, is the next project, even on the technical level. I mean, you made them black and white, which is curious. And I would like to see that what that means, because suddenly we have all the grayscale, all the values of gray in the thing. It becomes another visual thing, but that might also mean something. Because what I wanted to say it's so credible, this project. And if I wanted to question for a moment a little bit is, as you build up, there is of course the pressure on these creatures builds up massively. And so that's the first differentiation we want to think of. If there is blacks and whites, or maybe there is already, or a gray family where, because if you have large populations, and it's just a question of the concentrations of these, and you always have redundant ones, so the ones which go at the bottom are the black ones, and the ones at the very top will be the white ones, and everything else in between, or there's 3-4 categories, because that will be the lighter the top. That will be making a huge contribution to the efficiency of that. And we had the discussion earlier, so that's without even changing much in terms of the behavior, and they could still behave lots of things in the exceptional way. If there's shortage of whites, then the black goes on top. But once I've said that, you can see, what are the other subsystems, the other creatures. But we are just on the same level. We can be treated. I mean, you can bring us and these populations and social purposes of all this machinery into the model. And that's what I invite you to do, and that's what I need actually help with of doing also. But I mean, guys, it is stunning that after 2 days of incredible blow-away projects, you top it all with the kind of exponential shooting off that plateau of people. I mean, wow.
Look, guys, phenomenally impressive in every possible way, really. The only thing that disappointed me was that the play mode was so much less spectacular than everything else these guys did. But given that this thing is just a tour de force, like in every possible way, technically, I think it gets really, really interesting when we start to prophesize that we engage this kind of a system with program, right? So this is my house. I live inside, it's awesome. I decide to move in with my girlfriend, so we both break off a bit of this and we get rolled down the street. We come together, we now have twice as many blocks, and we build a new house somewhere. When we have kids, we rearrange them so we can have little bedrooms and things. Perhaps the alarm clock is simply that the bedroom wall dismantles itself just in time for me to make breakfast in my newly configured kitchen. And these sorts of things, I think, is really phenomenally interesting and exciting to kind of prophesize exactly what do you do when you have this level of the ability to redistribute matter. So go further with your stories about what these guys want to do, and explore the fantastic sci-fi world that you're really just one step away from.
I'm also a very strong supporter of the project. I think it wouldn't have been really possible in this first year of this brief to go beyond what you've done. I commend you on many levels of investigation there. So my comments now are imagining another iteration of this, right? And I would say it all starts with when we get to this model or any of these models on the table and any of the visualizations of a form. I actually would take a different alternative to David's, where I would imagine that I don't think its power is in that bedroom or that apartment. It's actually in that moving down the street. Like, it's in all the dynamic exchanges where the matter is constantly reconfiguring. So, for instance, a bus stop is often like an obstacle on a pedestrian. It gets in the way, it's a nuisance. But depending on the number of people there, there's a need for a shelter in the rain, particularly in London. So a dynamically reconfiguring bus shelter is an interesting thing. And then the question is, where do all these things go when they're not frolicking and having fun in the park? They probably run away and hide down drain holes. And then they just emerge when they're needed for bus stops, or maybe they become temporary umbrellas, just following people down the street, you know? Like, I'm not quite sure yet exactly what their purposes are, but I think it's not a question of one purpose. It's more just a whole series of situations, and each one is time-based, and there's just an ecology perhaps of how these things live in the city and interact with people and the environment. So I'm a bit opposed to the kind of monumentous architecture, but I'm strongly supportive of the animations that represent them.
Yeah, if I can add to, like, of course you should be commended for like tackling so many things. To the speculation, if I were to add, like I think like one trajectory it could take is the coupling of this with the environment, whether the environment has like humans or as Jason was suggesting, other machines. Right now it has sensors and it is responsive to the environment, but it doesn't register like a feedback mechanism yet. Like, so that could be the next hierarchy in a way, that wherever it goes, it deposits stuff, like, and that therefore like affects everything else that comes after it. Because you have already, you know, substantially showed like that the smart brick can already do all the things we want a brick to do. For it to be kind of ecological, perhaps like the next step will be like thinking of feedback and like its coupling with the environment.
Another thought, you know, you're inventing an entire sort of future here, and it seems right now that it's a highly mechanical future. You're proposing 100,000, 1 million of these things being sort of produced, and in their current iteration, they're still using kind of very typical kind of motorization. They're highly assembled. They'd be assembled on a kind of assembly line or something. It just seems that there's something for me really spectacular about this latest model. It looks like it was 3D printed flat, right? It was 3D printed on a flat plane, and and I'm not sure if you're doing it, but you could be 3D printing it with multiple materials, some rigid materials, some flexible materials. Certainly, your actuation could begin to be 3D printed also, using some kind of memory polymer or something. And so, I guess what I'm saying is that I think if you're going to continue with the research project, it's actually at that level. It's really not that far out there, because you'd really want to be able to produce these rapidly, right? And that certainly would bring up, you know, there's some really amazing folks right now looking at self-replication. How could these begin to actually participate in their own kind of reproduction? Which I think would be a really intriguing next sort of phase for the research, because, you know, you really want them, it's kind of like the renderings in a way, right? You've got this kind of reproduction happening magically in Maya, I guess it is, and you really want to kind of fulfill that. I don't know how, but I think there could be an amazing sort of next research. Maybe you spend your next year or so developing this as a kind of another agenda, because you've kind of got the swarm. It's sort of, we totally get the future, but now it's really a problem of kind of manufacturing, and actually maybe embedding sensing within that would be an obvious next step too. You know, literally 3D printing the sensors within the actual piece, 3D printing photovoltaic kinds of materials. So, and it's really not that far out there. There are labs that are doing that in isolated modes. And what I find so compelling about this research is that it, you know, I think actually the engineering field actually needs you guys. That's for me what's so amazing here, is they actually need thinkers that are thinking not down kind of funnels, but you guys are thinking in parallels, in meshes. And I think there are a lot of labs that are doing things in isolation, but not necessarily bringing it all together. That's why I think that this project specifically is really opening up, let's say, so much potential terrain. And there really are people in the world that would be very interested in this research. And I'm saying that in a very real way. This project is, you've taken it so seriously, and it's I think you guys should form a company. I think you all should move to San Francisco or move to, I don't know, stay in London, but come for, because this is a real, I think, a real thing. And it's really impressive to see.
A small point on what I like the analytics, the data which you kind of running on the background as a totally natural, as a matter of fact, that's what we do now. You continuously keep track of what's going on in terms of the energy use, the energy requirements, the update. So I think there's kind of data management infrastructure. There's a lot of bottom up, and but everybody, like you sell, is signaling out. There's also somewhere a central institution which gathers these data and collates them, dices and slices them, redistributes them to, and offers, new strategies and re-strategizing on how to climb and what to climb. So that's a very, very strong and powerful thing, and I think we need to see that. I mean, we all have novels and all our movements and so data mined, and there shouldn't be anything sinister about it. As soon as we manage really to get rid of the NSA, I think we shouldn't be worried about, service providers like Google and Apple and all those who make all this data collection fertile and feed us back and make all our experiences more smooth and fertile, let's say. This kind of collective intelligence in terms of the data sharing, data management and feedback network. I think is another vision which I find kind of slips nearly as if taken for granted implicitly in what we're doing.
Oh, no. Yeah. So just one more speculation on top of everything else. It's strange when we're dealing with pretty much an autonomous swarm of little bots that we can see recognizable structures. And I'm imagining that perhaps before you get to the book, that we could see one or two unrecognizable structures, but structures that are clearly operating under local logic, local rules, local associative conditions. You have all the coding there, it's all working pretty well in terms of things like the structural evaluation, the redistribution. But it seems that you are feeding in some very explicit goals at times. And I would just, in the next couple of weeks, do a few iterations where you abandon those goals completely and you really try to see almost in just a completely bottom-up way, not because it's necessarily going to be a better or worse project. I don't think it takes away from what you've done, but I think that this is suggesting something that is perhaps not so familiar, that we don't really know yet where to situate this type of work. And it would be nice to see it from a little bit of a different perspective than one that's not trying to fit it into what we already know, if that makes sense.
Maybe picking up on that. Conversation has continued about what the motivation is, and it's kind of round two. I think that there is an acknowledgement that this generation has worked on the individual component and tried to establish relationships. I like personally to see the 4 projects actually really highlighting very particular features, and what I commend these guys for is really they are the ones that are demonstrating population and the collective capacity for that with the kind of localized rules taking informed decision. So for example, energy is a criteria, and that creates a whole diverse spin-off of variety that's completely implicit on one constraint that changes and has to be evaluated on the scale of the population and the magnitude of that kind of very sensitive time-based kind of iteration. It's not spitting out solution spaces, but there's an acknowledgement that there has to be a learning criteria. And I think they are arguing in some capacity that that was based on structural evaluation, which is a version. And I think part of the thing is to try to tease out what are the other ones. if this is left to actually try to understand its context, and I think Patrick's first point for me was really on the head, which is humans are another population of an ecology. For example, we speculated that vehicles were another population that they would have to negotiate, because this isn't something that I want them to sort of hide out in the sewers and come out at rats, you know, like swarming and killing people. It's more about how do you embed this with a kind of criteria that allows these things to have adaptive features that can evolve. Its evolution, I think, is conditional to context. And part of the critical project, at least from my side, is to try to find a strategy which allows these kind of machine learning environments to become context specific. And I think that that's something that we're trying to talk about. I think it goes beyond mass customization as a subject, because I think that's been around for a while. It's really how do we use these embedded forms of practice and intelligence to try to problematize themselves first, acknowledge their awareness, and be able to iterate. Because I really do think the adaptive feature is very much tied to humans. And this thing spitting out iterations is not necessarily to be domesticated for human approach. It's actually to invert that and to understand that the way that we occupy space, the way that we explore it, the nuances of these things, which are very animate, have very particular communication features, and how to exploit that in a meaningful way that really will allow this stuff to actually do the kind of promise of a human interface with machines that actually establishes goals not as a prescriptive method, but actually as something that's kind of evolving. I think that that's part of the plan. Now, the promise of this kind of stuff is about demonstrating, because as soon as they get 2 or 3 of these things working, the higher populations of these things, based on that rule set, give some legibility. And I would encourage you not to think like a startup, like completely, because I know a lot of people have the objective to take something and to put it out there. But between the projects and so forth, I think it's a community of people that are actually thinking that this is important from the architectural perspective. I'm not really interested in people that see it from another perspective. This could be a product, it could be a toy, it could be a vacuum cleaner. Rodney Brooks is an amazing example. His history of research in robotics, particularly because I had an office above the MIT Museum, to see that lineage and the speculation of where that could go, and to realize that basically the thing that in one sense gave him the most monetary comfort was the little Roomba that they guys created to just kind of go out in a passive way and to vacuum. I think that there's a much deeper speculation that's possible, and that's why we open up this process to other people, because Brett had made a comment about how to put this out in the world, and I think it is a much more dedicated conversation, and that's why I think having people that are in the room here may be interested in this stuff, you guys doing your thing, we do our thing, and I think there is a 2.0 and a 3.0 and a 4.0, and I think that that's really important, and you guys should be active members of that community, because I think your knowledge is not tied literally to this prototype, but it's tied to that whole process of discovery, and to share that is not a trivial thing. It's a very motivated, we talk about motivation, attached to the fact that you think that there is really a general sense of purpose of what you're doing, and you feel that that's important enough to share it and to open it up in a conversation to take the next steps. And I think that this is important. It's something that we have to talk about. What is round 2 of an agenda? Because we've been working on these things. We open it up to you guys. We open it up to others. And at the same time, we also have to be critical. And that's why I really like to see the 2 days of really having an influence between the different studios, between the different projects. Because I think that there are things that these kids have to highlight and really bring in terms of the discourse and the way that we work on these projects. Like the vision systems that Rob was working on, Sajay augmenting some of the industrial robotics, because some of these things are scalable and some of them aren't. And I think this kind of acknowledgement is a really important thing. And I think that's how we sort of upgrade the profession, which I think really, really needs it. And since today is a graduate school open day, and kids who are kind of sitting in here thinking that this stuff is really inaccessible. 16 months ago, these kids didn't know any of this. And we're not computer scientists, and we're not salesmen trying to make a pitch for you to come here. But if you're interested in this kind of stuff, it's accessible And if you're motivated to do that stuff, then I think it's much more appropriate for people to actually work through these problems, because I think, we don't have robot culture here. Greg is our consultant roboticist, but even that, I mean, a KUKA is one version and this is something else. And there's a family of conversation, I think, between these things that actually see it part of a much bigger future. And today we've kind of extended the day by an extra 2.5 hours, and we're going to have a lecture here, which is a keynote of Jason, who has the honor of closing this session. And I think we should bring today to a close in this capacity. I'm going to ask you kindly to go outside so we could organize the chairs, and then we kick off with our keynote lecture. Okay? Thanks, everybody, and to the critics.